Yeah, okay. I also have a lot of slides, so just get started. I'm Thom Wiggers. I work for PQ Shield, and I have in the past life been doing a PhD, and in that PhD I studied post-quantum TLS. And this talk is going to sort of serve as maybe a reminder from the sort of more practical community to the research community on how the deployment of post-quantum TLS is going. And I'm going to talk about maybe the hardest challenge that we're seeing in boring cryptography, at least in the TLS space. So yeah, I work for Big Shields, but that's not so interesting. What is interesting is that we're talking about this today. So TLS is probably the most used cryptographic protocol. Your phone probably has more sessions open than you have fingers. Even if you're not browsing the internet right now, it's basically the back channel for every secure communication that we're using. We layer a lot of stuff on top of it as well, but yeah, TLS is very, very ubiquitous. Yeah, this is the wrong slide deck. Okay, I'm gonna have to do the skip a lot of slides version of this talk. Post-quantum, right? We know why we're here. We also know that NIST did a bunch of things, and they have given us a bunch of standards, which is very nice. And we know that TLS looks like this. So TLS, as I said, is very boring cryptography. Look, pointer. There it is. So we have a key exchange of the most boring variety, a Diffie-Hellman key exchange. We have some signature that signs that key exchange. I mean, it's very, very straightforward, very boring. We can make that post-quantum just by crossing out a bunch of things. We just write a post-quantum key exchange instead of the Diffie-Hellman key exchange. We just write post-quantum in front of signature so that we have a post-quantum signature. And yeah, what more is there to do? We don't even need to use AES because AES, I mean, 128 is probably fine. So the main question is, what things do we fill in those things that we crossed out? I mean, NIST have graced us through a long and arduous process with what they now call machine learning modular lattice chem. And the smallest version is, I mean, it's a bit chunky, 1.5 kilobytes of data to exchange, which is a bit more than the 64 kilobytes that we're used to, but I mean, maybe not entirely terrible. And then we have a bunch of signature schemes, and I mean, this is the 3 algorithms that have been selected. Unfortunately, we're sort of stuck with the lithium probably for most use cases because of side channel concerns with Falcon. But yeah, we're looking at 3.5 kilobytes there. But I mean, maybe we can tank 3.5 kilobytes. So we also know that Chrome is already doing this. So if you have Chrome 124 or later, and that came out in April, so you should be on later, then you should be using post-quantum key exchange, or at least your laptop will try to negotiate post-quantum key exchange in Chrome desktop. And if you connect to, for example, Cloudflare, then due to a lot of effort of Bas, who will be giving the next talk, then you should be getting post-quantum key exchange. In fact, we're already up to 26% of all TLS connections that Chrome desktop is using, at least for the average user. Google reports that that is using hybrid key exchange with Kyber 768. So we're done. We know what to do for the certificates. Yeah, what else is there, right? Signatures. We have a big elephant in the room, and that elephant is the Web PKI. So with the Web PKI, I'm referring to all of the infrastructure that we basically need to trust that the server is who they are. So that's the certificates, more or less. The certificates specifically for the open internet. So I'm not talking about any private PKIs. I'm not talking about what a particular organization is doing internally behind the firewall. I'm talking about the certificates that you use to connect to example.com. You have this button in your web browser somewhere, view certificate. And if you click on there, then you see that actually we're talking about a bunch of certificates. If you cross the internet, you need to get a certificate from a website. And usually what you're getting actually is not just this bit at the bottom, with the handshake signature that actually signs this website visit, but you're actually getting also this intermediate certificate that's there basically for management reasons, and the public key and signature that are associated with that. So instead of just sending over one public key and signature, already talking about 2 signatures, 3 signatures, and 2 public keys. So if we multiply that with 2.5 kilobytes per signature for the Lithium 2, then you see that the numbers are going up quite quickly. CAs, I mean, they get instituted by spending a lot of money on audits, and you convince the vendors to install your certificates, and then they sort of arrange signing for us. On the surface, this seems very easy, but I mean, the PKI is actually quite a bit more complicated. We all know that the hardest problems in cryptography, cryptography is a tool to turn questions about confidentiality into questions about key management. So how do we issue certificates? Certificate revocation is a big problem. And we also have sort of this problem that if we just allow any CA to issue certificates for any websites, how do we prevent situations where, like the DigiNotar attack, Iran hacked the CA and made them issue certificates for gmail.com. So any problem in TLS has more or less been solved by adding yet more signatures. And in these 2 examples, I mean, the online certificate status protocol basically tells you this certificate is currently not revoked. And the way that that is done is if you use OCSP stapling, is that you, as the web server, you go to the issuer of that certificate, and you ask the the CA for a proof that you can include with all of the requests that are coming in that says, currently, this certificate is not revoked, or at least in this time window, this certificate is not revoked. Yet another 2.5 kilobytes. Certificate transparency is the system in which we sort of log all of the certificates that are issued for all websites on the internet. So in that way, Google can monitor that log and see which certificate authorities are issuing certificates for gmail.com. And Chrome and Safari, they require each certificate to have a bunch of these inclusion proofs in these logs. Most people use 3 of them instead of the minimum 2. So that adds 3 times 2.5 kilobytes to each handshake if we're using the Lithium as a drop-in replacement. So yeah, that's quite bad. Yeah, this is certificate transparency. Transparency works by building a nice Merkle tree out of these certificates. I'll get to some of these details a bit later again. If we look at the typical TLS handshake, sort of summarizing all the things I've just described, is that we have, we have a key exchange. That's sort of the point. We're trying to do an authenticated key exchange, so let's keep that part at least. But we also have a handshake signature and the public key for that in every single visit. So the key point about that thing is that it's online. I mean, you need to do this for every single exchange. And we have a few things that we can sort of refer to as offline certificates. That's just basically static list of bytes that happens to prove that you own that certificate and that's currently still valid, and the certificate transparency stuff. Maybe we can use a bit more different algorithms for them with the right trade-offs. That leads me into what would this look like in the post-quantum setting in terms of performance, the really practical stuff. So if we just adding post-quantum key exchange, if you use the smallest parameters, you're looking at 1.5 kilobytes of extra data. So that's not too terrible. There's also not really a way around that. If we're looking at replacing all of the signatures in the handshake with MLDSA, formerly known as the Lithium, then we have 18 kilobytes of certificates that we need to transmit with every single website visit. And actually, in a single website visit, you're probably opening about 10 to 15 TLS connections. So that gets quite painful quite quickly. And even if we use Falcon, then we're looking at 5 kilobytes of data additional. The annoying thing about 18 is that it's above the congestion window default. So that might lead to extra round trips, but even before that, we know that more data is more slow. We know that because Bas did some experiments. This is a very, very nice blog post that he wrote that I keep referencing basically everywhere I go. But we see that if we would sort of add the lithium, then we see that we get a 25% to 35% slowdown. And this experiment probably measured more bots than actual users, so there's a good chance that the actual results might be slightly worse. Also, we see here it's better visible in this graph. You see here the big jump in sort of the congestion window, because Cloudflare has that at 40 kilobytes rather than at 10. So it might be that this for the average user that might be more living there. So we don't want to add that much data to TLS, and that is sort of backed by the results that are coming in from Google. They've used Kyber 768, not Kyber 512, so they're adding 2.3 kilobytes to every handshake. And they observed that this already on Chrome desktop, so computers that's probably connected to good Wi-Fi, powerful chips, well connected to the internet, that already slows down handshakes, connection establishment in TLS by 4%. They also note that they observe a significantly higher impact on lower quality internet connections in general and phones in particular. This is why it's only turned on in Chrome desktop and not on Android, even though they've also experimented with that. Turning it on Android, they write, basically makes the internet too slow for those users right now. Google also sort of give us a budget. They say that to stay under 10% of slowdown, we need to stick to at most 10 kilobytes of additional data for post-quantum key exchange. And that includes the key, not for post-quantum key exchange, for the whole post-quantum thing. So key exchange and authentication. And that basically means that we need to do something better than just replace all of these signatures. It's not just about speed. I mean, there's also some implementation bugs that we're running into. Fun websites is TLDR.fail, but basically larger hello messages can lead to fragmentation. Basically, the key doesn't fit in one packet anymore. And not all implementations are prepared to deal with this because it never happened, right? The spec allows that this happens, and it says that you need to deal with this if this happens, but a lot of people are like, yeah, but people using elliptic curves, that no, it's not going to be a problem. And of course, it's now a problem. And as people trying to run experiments, the Chrome gets an update, your internet breaks. Who are you going to blame? Probably not the firewall box that's been sitting there without an update since 2015. So that is somewhat problematic in these experiments as well. And we're going to have to sort of fix this, and we're just seeing this now with the client hello messages, but the sort of question is this going to get worse if we also add a lot of data to signatures? So we want to avoid the cost of certificates. We know that they are already quite large. Post-quantum makes this much worse. I mean, we're already talking about transmitting like 4 kilobytes of data, even with RSA keys. Most of that is not actually in the RSA keys, but adding an additional 18 kilobytes is just very, very annoying. But we also sort of observe that we have a lot of signatures there, and a lot of them are kind of proving the same thing. We have the signature on the actual leaf certificate, the actual example.com, and that proves that that certificate, that public key belongs to example.com, right? But we also have the OCSP staple that proves that this certificate for example.com is currently valid. So sort of the same thing, but additionally with a time window. Certificate transparency logs only accept pre-certificates for inclusion if the issuer for that certificate is on the CA, the list of CAs that transparency log trusts. So the inclusion proofs by themselves also sort of prove that this key that belongs to example.com was trusted by a CA and include it in the certificate. So we have a bunch of signatures that are sort of doing the same thing. So the question sort of becomes, can we do something smarter? So do we need to redesign the web PKI to make post-quantum work? And it turns out that we're going to have some space for design. A more conservative approach is maybe to just combine different algorithms. I already alluded to this a little bit, but we can sort of pick and choose algorithms to fit in the roles that they serve. So for the online part, the handshake signature, the signature that you need to produce on every single website visit, we need something that is robust against side channels because it's going to run on a lot of different devices. Not all of them are going to be very protected. And probably Falcon is a little bit hard to deploy in that scenario. So let's just stick with MLDSA there. The sum of its public key and signature are big, but not super big. It's nice and fast, so it fits well in that role. For the signature by the intermediate certificate on the leaf certificate, we're going to need an algorithm that has a small signature and public key as well. But that's a signature that we're just sort of statically transmitting every time. It's embedded in these certificates and it's public key as well. So can we maybe avoid the side channel problems by just hiding it in a big vault, putting a fence around the vault, then adding some guards around the vault, and then everyone who shows up with an oscilloscope to measure the timing invariance, we just shoot them. Maybe a bit radical, but maybe a way to deal with this problem, right? So maybe we can use Falcon in such cases. Very limited deployment, but it might be a way around sort of the side channel issues there, because Falcon is very nice and small. And then we have a bunch of cases where we only transmit these signatures. And in the case of certificate transparency, we only have a few logs, so not so many public keys. So maybe we're tolerant to algorithms where the signatures are very small, but the public keys are very big. So UOV is an example of this, obviously. We can just pre-install those 300 kilobyte public keys or whatever the size is of the latest variant. And we don't need to transmit them anyway. We could just include them with the software. Maybe this works. But I mean, aside from the fact that we're still using the lithium and the lithium is still quite big, we still have a lot of signatures, and using multiple algorithms has a lot of cost. So more code, more surface area for bugs. In embedded settings, we need to ship all of this code as well, and smaller devices don't necessarily have a lot of space for them. So it's an attractive thing to investigate, but it also is annoying. Also, the certificate authorities are very not hype about this because they don't like buying lots of expensive equipment for lots of different algorithms. So they need to buy everything in like 3 different variants as well. So, and of course, the management overhead that comes with all of this. So worth investigating, also not easy. Even this is not easy. Another example, another proposal that has been put forward by Mozilla, by Dennis Jackson in person, was to basically try to compress this chain of certificates. So instead of, it's a 2-step process, and the first step is basically realize that maybe we can also just put this in the web browser. Just like we're already shipping these, how about we just ship both of these and stop sending all of these intermediate certificates that are basically there for management reasons, and include them with the web browsers. We have mechanisms in web browsers to update things. You download a new version with latest code fixes anyway every month. So we can probably get away with including them. This has been proposed a bunch of times. Usually people have complained about, yeah, but then you're sort of need to indicate which intermediates you have. But the way that this draft works around that is that we sort of designate the 2024 list of intermediate certificates is this list. And then the client can indicate, I have list version 2024. And then the server can sort of interactively decide, okay, you're up to date enough that I don't need to include this intermediate certificate. And that way we sort of get a nice fallback for clients that aren't out of date. that are out of date or something. This immediately saves one signature and one public key, right? So that's kind of nice. This doesn't really get rid of all of the certificate transparency signatures and all of that, but it is a nice first step. The second step of this two-step program or three-step program is to basically just run zip over the thing. It turns out that there's a lot of strings in certificates, like the name of the issuer, policy URLs, the URLs of transparency logs, that are pretty common, but also very long. So there's a lot of boilerplate. We already have a mechanism to compress certificates. So there's an RFC that describes that you can negotiate use like Brotli or zlib or zstandard for compression. But this draft makes that a little bit smarter still, basically by realizing how these algorithms work. Namely, if you recall your data structures course that you probably took at some point, maybe very long ago, the way that compression usually works is that you construct some sort of dictionary, and then strings that occur in two places, you basically replace them by a pointer into the dictionary. And because this draft basically already proposes a system that allows you to indicate what version of the list of intermediate certificates is, what if we build on top of that, that we also, along with this list, we ship a pre-trained compression dictionary, and then we not just indicate the version of the list of intermediates, but also the version of the compression dictionary that we have. And then we don't need to send the compressed certificate as this plus this, but we can just send this instead. So that actually leads us to quite a lot of savings. So this is a nice table from the draft, and the average certificate is, or the average list of certificates that a website that is exchanged in a website visit is 4 kilobytes, and it manages to compress that all the way down to 1 kilobyte with RSA certificates, right? So the keys are not being compressed. I mean, keys are high entropy. If we knew how to compress those, we would already be doing that as part of the algorithm. But this sort of shows how much craft there is in the certificate system. And if we sort of manage that a little bit better, then we are able to get rid of 3 kilobytes of data. So that's pretty significant. It basically gives us space for 1 dilithium. But we need more signatures than 1 dilithium. The nice thing about this proposal is that the analysis is very easy. If we just uncompress everything, reinsert this intermediate certificate, we get the thing we started with. So we don't really need to spend a lot of time on security analysis because it's sort of easy to see how this reduces to the security of TLS. The next proposal is more complicated. And the core of this proposal, on which BOS is also a part, is that we sort of restructure the entire PKI. And what I like about this proposal is that it's pretty radical, and it shows us, especially the academics, actually the amount of design space that we have right now. I mean, the previous proposal basically looked like engineering. This is starting to look a lot more like cryptography, cryptography research. So the idea is that we replace the entire PKI by a completely new system, or at least as far as the web browsers are concerned. So we have certificates, and these certificates are issued by a CA, and that CA is called Thom Trust. And what we're going to do with those certificates is that we're going to lay them out in a Merkle tree. So we just put them all next to each other and build a nice Merkle tree. We've seen those before. And then we create this tree head, and we sign that as well. And now we have a Merkle tree that has all of the public keys and the names for all of those websites. Then what we're going to do is that the web browsers are going to take all of these Merkle trees by all of the different issuers, Thom Trust, Bassert, that's Eckert, In joke for the TLS crowd. And the web browsers are going to take this list and audit that they were constructed correctly, check if the transparency stuff was done correctly, because that's also part of the design. And what the browsers are going to do is just ship out all of these tree heads to the web browsers directly. So the web browsers now have all of the Merkle tree heads for all of the issuers that they trust. Then in step 3, I mean, this is how the usual TLS handshake looks like, right? So we ask for a website, then we go to the website and we get their public key and a certificate. But what we're now going to do is, instead of the certificate and all of the associated data like OCSP and SCTs, is that we're just going to send that public key directly with the Merkle tree inclusion proof. So the path in the Merkle tree that leads up to the tree head, so we can authenticate that that public key was part of the certificates that were issued by that CA. And we just get rid of all of the OCSP and the SCTs. Why can we get rid of all of that that additional information? Why can we get rid of transparency? Well, that was audited by the web browsers before they pushed out these tree heads. Why can we get rid of the revocation information? Why can we get rid of the information that the certificate is currently valid? Well, we just do this every hour. So this is quite involved, right? You need to not only run that entire system, but you're also committing to instituting an update process that requires all of your clients to fetch all of the new information every hour. Of course, this fallback, I mean, if you're going to indicate I have this version, I am this up to date, and then the web server can decide, oh, right, you're not up to date yet. I'm just going to send you the slow version now and spend a few more bytes so that you can still connect to the website. But I mean, even just the web browsers, for most of their clients, they're going to have to run this process, run all of these audits, and process all of these new certificates, and do that very, very, very often. But the upside is that we can do this in well under, I mean, this 1,000 bytes is probably an overestimation, well under 1,000 bytes of authentication information. And that addresses, I mean, we're replacing all of the signatures that are there to authenticate the public key, right? So this is very, very significant, both in the design, how involved it is, but it's also quite significant in the sense that the savings seem very worth it. And it's immediately post-quantum because Merkle trees are hashes, right? So we don't need to worry about breaking RSA or breaking elliptic curves. So yeah, this seems like a very promising thing. And as you maybe saw, this is being proposed right now by a team from Google together with Cloudflare. So we're talking about real world cryptography, I think, here. This is not something that some academics have dreamt up in a nice ivory tower in the English countryside or wherever. This is a thing that industry is actively pushing right now. And I also think that, I mean, you can see that this proposal, I mean, also this part of the proposal is pretty radical, it's pretty involved. So I think there's space for other ideas, maybe if not in TLS, then also in other spaces. The problem here, I mean, it's a big change. We're going to need short-lived certificates. The web server needs to continuously start fetching all of this information, but not just the web server, but also, the web servers and the clients are going to need to fetch this information all of the time. The web server, because they need to be able to just give the latest version of the inclusion proof. The clients, because they need to keep fetching these new tree heads. Stuff like Acme is going to help with this. So the software that we use for Let's Encrypt basically already lets us get new certificates every 3 months in an automated way. Maybe we can sort of reuse that sort of system and run it every hour. But yeah, it's also a very new trust model, right? We're moving things between different spots. The Merkle tree is a new way of doing things. It's not just signatures anymore. This makes even just describing which security properties we're going to need exactly it's much more like an analysis of certificate transparency than it is an analysis of a chain of signatures, right? So it's very different. The common theme between these last two proposals is that they are designed for big deployments. I mean, even the list of intermediate certificates, if you're not on the list of intermediate certificates, you're not going to be able to make use of being on the list of intermediate certificates. So then you're still going to have to send all of that data. If you run a private CA, you're never going to be on any of these proposals because the web browsers will not audit your private CA's Merkle tree because they don't have that information. And also, I mean, you probably ran a private CA because you didn't want to pay for a CA to begin with. So yeah. What about the IoT setting? Is your smart light bulb going to commit to updating its Merkle tree heads every hour? What is ABN AMRO Bank going to do internally? So that's all still unsolved questions and unexplored areas of this design space. What I was just talking about was really aimed at the web PKI, and we had TLS in a lot more places than just on the public internet. I mean, we use it for VPN. In OpenVPN is basically TLS. We have it, more places than you can probably even imagine, because TLS in cryptography, like in the ITF, for example, it's basically IBM. Nobody ever got fired for using TLS. So yeah, we still have signatures in the handshake, right? So what if we want to go even lower? This slide is all I'm going to talk about this, but ChemTLS was a proposal that I worked on in which we replace signatures in the handshake completely. So instead of signing the handshake, what we're instead doing in ChemTLS is that we do an key exchange instead. So basically the idea is, instead of proving that you have the secret key that belongs to the public key in the certificate, we're going to encrypt something to the public key in the certificate, namely a ciphertext, a chem ciphertext. And by proving that you can get the secret that's in there, we're able to authenticate you. The nice thing is that this brings the complete cost of authentication down from 3.5 to 2 kilobytes if we're using MLChem 768, or from 3.5 to 1.5 kilobytes if using Kyber 512, MLChem 512. But there's some other interesting algorithms like BATChem, which is not a NIST proposal, not something that was part of the NIST competition, but an algorithm that's kind of nice because it has like a 1 kilobyte sum of public key and ciphertext. BAT is unfortunately very slow for key gen, so it's probably not so nice to use for ephemeral key exchange, but in this case, we're talking about static keys, right? So this could maybe be very interesting if we want to go really low in terms of size. On the other hand, this is a very, very big redesign of the TLS handshake. And as the person who did the redesign, I'm also the first person to admit that it is a very big redesign of the TLS handshake and all of the security properties that we have there. So I like to say that I did my analysis very carefully, and we have like proofs in Tamarind and pen and paper and whatever, but still this is like a big change and needs to be looked at very carefully before we widely deploy this. But we're also in the ITF, so if this is something that you're interested in, you can also look at what we spec'd out there. That sort of wraps up my talk. So even though TLS is maybe boring cryptography, the constraints make this very, very non-boring. I guess in many ways, the Signal also has concerns like this. Chems are less flexible than Diffie-Hellman. That is not so much a problem for TLS as so much as, for example, PQXDH. The Diffie-Hellman operations in X3DH from Signal, which are used also for the authentication with the identity keys. If we had non-interactive key exchange instead of chems, then we could just plop in a different primitive there, but we don't have that. So some protocols will need to be redesigned. Even if TLS doesn't need to be redesigned, we know that they are quite a bit bigger than the elliptic curve crypto that we got used to, and this is particularly true in the signatures case. But it's not just the protocols themselves, it's the surrounding ecosystems that we built on top of those often cheap signatures, the cheap key exchange that we especially have with elliptic curves, we might need to reconsider some of those designs. And that sometimes might mean that we are willing to trade sort of operational complexity for and protocol complexity for sort of the operational cost of these sort of things, in cost in terms of bandwidth. For some applications, it's going to also be cost in terms of the computation time. But certainly slapping another signature in it is no longer a cheap solution. The web PKI right now is considering very big change, I would say. And it was even to me sort of surprising that they were open to this level of radical new proposals. And I think that that is actually very exciting because it gives me a lot of new ideas to think about, a lot of new security models to consider, and basically ensures that I work for a couple of years still. But it's also, I think, an opportunity to see what other people can do. And if you have bright ideas, you might find that there is more of an audience for them than you would have maybe thought a few years ago. Yes, this is probably not true for just the web PKI, but maybe also for other spaces. Bas is probably going to refer to this design space a little bit more. Actually, I've talked with Bas about his slides. He's going to talk about this design space a little bit more. So yeah, the hyping up of Bas talk out of the way. Even with all of this redesign of the PKI, we might still need more protocol redesign to get under this 10% slowdown. Basically, my Ken TLS advertisement of this talk. And that was it for me. So I will answer to the best of my ability questions about TLS. Yeah, thanks for your time.
Please raise your hand if you have any questions.
Thank you very much. This is a very good talk. My question is, in IETF, to make a PQC transition, there are some proposals about using hybrid schemes, using both PQ and non-PQ schemes. Can you comment about this? Whether they will become a common solution, or this is just occasionally have it as a temporary case?
I have the impression that basically everyone is currently only talking about hybrid replacements for certainly key exchange, but also for certificates. Mike Ounsworth in the LAMPS working group that sort of governs how X509 works has been putting forward a lot of proposals that combines classic signatures with post-quantum signature schemes. There's a lot of discussion about the shape of the hybrids, but the general sense is that most people, and indeed in the experiments that have been deployed right now, people are combining elliptic curves with post-quantum. There are certain people that are less interested in hybrids. I mean, the NSA is probably the most famous one because it seems that they are scared of having to move twice. It seems that the web browsers are in a position where they control a lot of code, right, on the endpoints, and they have already, because of the way that basically for software security reasons, they have very mature update processes in place. I mean, both Android phones and Mozilla, Firefox, and Chrome and Safari, they basically have processes in place that every time they sort of connect to the internet, they check, do I have the latest version of everything? Do I need to download any urgent security patches? Do I need to disable any scary features that have maybe been so that infrastructure is there, and that probably gives them a lot of confidence that they can maybe do this twice and get rid of the elliptic curve stuff later. I can't comment on all people and all deployments, but I mean, if you're deploying a smart light bulb that's gonna, or a smart car that's gonna be there for a very long time? Are you going to immediately go to full post-quantum? Are you gonna go with hybrid for the next 30 years and committing to that instead? It's hard to say, but certainly most people, at least in the sort of online public internet setting, do seem to be considering hybrids, yes.
The industry seems to want to take a safeguard. NIST seems also to suggest the hybrid is possible, the safe solutions. Yes, maybe you're right. It's not both ways. You have to go one way or another. Maybe everybody can make their own decision, but most of the people don't want to make their decision for the crypto. Thank you. Thank you.
Yeah, I think sort of most people are sort of recommending hybrids, and it seems that, I mean, the nice thing about sort of the upgrading TLS is that, I mean, it's very exciting for us cryptographers to think about, but for most people, this is going to be a component that's part of a larger system that's just going to be updated for them. So OpenSSL will probably decide to implement hybrids, and a lot of people are not even going to realize that to use a post-quantum key exchange. Even those developers that are linking OpenSSL into their own libraries. So yeah, I think that we'll see how that develops over time.
Okay, so we have one question by Simone on Zoom. Thanks for the presentation. I was wondering about the impact of a hybrid PQC plus classic crypto transition for TLS. Is it an option? So I think it's related, but I think it's asking about the impact of that.
Yeah, so the figures I quoted of the 18 kilobytes is 18 kilobytes on top of the keys that we have right now. So assuming that we're not being dumb and combine RSA, we don't combine RSA with the lithium, but we're going to just combine elliptic curve signatures with the lithium. You're sort of adding 60 to 100 bytes to the figures that I added. So it's a little bit of noise behind the comma, you could maybe say. So I don't think that hybrids are necessarily much more expensive than, at least in terms of bandwidth, than the pre-quantum setting. So the nice thing about Merkle tree certs is that we don't really need to care about this because it's all hashes all the way down. So we just use them and don't need to have this discussion. So that's a nice upside of Merkle tree certs.
We have any other questions? Actually, I have one. So when in your slides, it seems to me that it's mostly like web browsers that are really pushing for this. What are the CAs, thinking about it? Do they want to do this right now, or do they just want to? Yeah, what's their position on this?
The CAs like selling new things. So in that sense, getting on board with post-quantum is certainly a new thing to sell, and they certainly do have interest in doing this. I mean, they also have customers asking for this, so that's probably going to happen. I think the CAs are waiting for NIST to get really finalized. They need to buy validated hardware, and no one's going to be able to sell them validated hardware until NIST is done. But I mean, certainly in sort of the mechanics, they have been putting things in place. So again, Mike Answorth in the NIST LAMPS working group has been sort of doing the certificate mechanics. And if that is in place, in theory, as far as TLS is concerned, we just need to add like we support this line to the protocol, and then the rest is sort of handled by that layer.
Okay, thanks. Are there any other questions? If not, let's thank Thom again.